All right, class, we're going to continue on our study in Chapter 2 about matter and atoms by looking at molecules and compounds. Now think about this. Let's say you have a piece of wax. If I cut it in half, is that half still wax? Well, how about if I cut it in half and half and half and half again? Is it still wax? The question is, when does it stop being wax? When is it only part of it wax and the other part is something else? Well, what we need to take a look at is what really makes up a molecule of a compound. Well, let's look at this slide for a second. What we see here are different molecules of certain gases. There's one H2 molecule. This one is one O2 molecule. If I have hydrogen gas and oxygen gas together, I have a mixture of hydrogen and oxygen molecules. A molecule is a group of atoms chemically bonded together. Now you'll notice that these molecules are bonded together and they're the same element in that molecule. But if I have a different element in the molecule or two different elements, then I have a compound. For example, over here I have elements bonded together. But in this compound, I have hydrogen and oxygen bonded in the same molecule. So I call this molecule, it's a molecule of a compound. And a compound is a substance containing more than one element which is bonded together. So that's the difference between molecules and compounds. Now let's take a look at these things. What do you think all these things have in common? Now, to be sure, when we look at gasoline, I just want to focus on one thing there called octane. And if we do that, then they all have something in common. What they all have in common is they're made up of only three types of atoms: carbon, oxygen, and hydrogen. Some of these, like candle wax, may only have carbon and hydrogen in them. Gasoline or octane has all three. Plastic. Most plastics have all three. Some plastics have additional atoms, but they're made up of carbon and oxygen and hydrogen, at least this flimsy kind of plastic. And aspirin is a compound that's made up of only carbon, oxygen, and hydrogen. Now think about that. Think about how many different elements we have in the periodic table. Think about how many different letters we have in the English language. And using only these 26 letters, we can make up more than 200,000 words in the English language. That's one language. I like to think of chemistry as the language of love. It's what makes everything come together. And with these so-called letters, all these elements, these individual symbols, we can make up trillions of substances that make up the entire universe. All right, now when we look at a molecule, we want to represent it in a way that everyone understands it. So notice here with water, I've got a hydrogen, I've got an oxygen, and I've got another hydrogen. When we write it, though, we write it as H2O. Notice there's a couple things. First of all, you've got the elemental symbol. All right, we also have a number that's kind of subscripted below the hydrogen. The subscript means there are two, in this case, of the element that comes before it. So H2O means two hydrogens. When we don't have a subscript after the O, we assume it's a 1. Obviously, there has to be at least one, otherwise we wouldn't have included it in the chemical formula. So H2O means two hydrogens and one oxygen. It's really important to remember that the subscript comes after the symbol for the element that it pertains to. All right, there's another compound that we can look at. This one here, sodium hydrogen carbonate or sodium bicarbonate. Now, right here that I'm putting in a box, that's its chemical formula, NaHCO3. Just above it is its structural formula. You can see how each element is bonded to each other. The formula gives us how many are in the compound, how many oxygens, how many carbons, how many hydrogens, how many sodiums. But it really doesn't show us much about how they're bonded together. So sometimes it's beneficial to have a structural formula in addition to that. I hope you can see again the subscript here, that 3 is for the oxygens, and you can see that we have 3 oxygens in the compound sodium hydrogen carbonate. All right. Now, let's try and do a little practice. Write a chemical formula for a compound that has 3 hydrogens and 1 nitrogen. Now, we don't know too many rules about it, and that's okay to practice. When you first learned any language, you just practiced. When you were a little baby, you tried all kinds of words, and some of them, probably most of them, weren't words at all. But your parents encouraged you anyway. They said, "Oh, you're so smart. Good job." And so here, I might think it's H3N. So I write H3N. That's okay. That's okay because this correctly shows a compound with a chemical formula that has 3 hydrogens and 1 nitrogen in it. It turns out the compound that has 3 hydrogens and 1 nitrogen in it is called ammonia, and it's written NH3. Now, we'll get into why it's NH3 instead of H3N later, but just know that if you did H3N, that's okay. You're all right. You're doing the right things. Okay. Now, the properties of a compound depend on more than just the structure of the molecule, or let me restate it. They depend more on the structure of the molecule rather than on what's in it. For example, we saw all those examples of different kinds of substances with just carbon, hydrogen, and oxygen in them. But it's how they are bonded together and what the structure ends up looking like and how it's shaped that determine the properties of the compound. It really does matter the order you put things in. For example, these letters up above could spell funeral or it could spell real fun. There's a big difference. In the same way, chemical compounds, look at these. These all have the same 3 elements in it, and they all have the same number of each element in the compound, but they are all very different compounds. So the arrangement that they are in the molecule really matters. Now, how do we represent molecules? How can we represent them? You can see here we've got all different ways of representing heads or faces. Well, we have different ways of representing molecules. The first and easiest is just the chemical formula. There it is, CH3COOH. But again, that doesn't show us much about the molecule. If I want a little bit more information, I write out its structural formula. Now, for you and your background right now, you should probably be okay with the fact that you don't know how to write the structural diagrams for them. That's okay. That's my job. But pretty soon, you're going to get more and more familiar with different molecules. Then you should be able to write structural diagrams. Now, another way of representing this same molecule is with what we call a ball and stick model. We can see the sticks are the bonds and the balls are the atoms that are bonded together. If we really recognize that the atom is more than just the nucleus, but it's surrounded kind of by a force field of electrons, we talk about a space-filling model, or even the molecular surface model, where the surface represents the force of the electrons repelling other molecules away. And so this shape of that molecule really extends out beyond just the atoms itself. All right. Now, there are some things that we call molecules, and there are other things that we call ionic compounds. When we have an ionic compound, we have ions that are bonded together by a transfer of electrons, and these ions, in its crystalline form, just keep going on and on and on. There's not a discrete molecule. In other words, we can break sodium chloride or salt down into just 1 sodium and 1 chloride, but really this table salt crystal keeps going on and on and on, not just in 2 dimensions, but actually in 3 dimensions. And so it's not a molecule. A molecule is bonded not by ions or transfer of electrons, but by covalent bonds, and it has a specific end structure. In other words, this is one aspirin molecule. It's the smallest piece of aspirin that you can get, and all the atoms are bonded by covalent bonds within the molecule. So ionic compounds, strictly speaking, are not molecules. They are formula units of ionic compounds. So if I write NaCl for sodium chloride, that is one formula unit of an ionic compound called sodium chloride. All right, so here's some vocabulary that you need to have down. An ionic compound. It's a compound that's stuck together with positive and negative ions that are attracted to each other because they are oppositely charged, and they become oppositely charged through a transfer of electrons. A sodium atom transfers an electron to a chloride atom, so we get a sodium ion and a chloride ion. And once that transfer occurs, then the sodium is positively charged, the chloride ion is negatively charged, and they attract each other. An ion is simply an atom or a molecule with an overall positive or negative charge. All right, now here's another really, really important skill that you're going to need to learn how to do. And it's about calculating out the formula mass of a compound. Let's look at water, H2O. I recognize that in H2O there's one hydrogen atom, two hydrogen atoms, and one oxygen atom. So we have in one molecule one oxygen atom and two hydrogen atoms. Each one has a certain mass. Remember, we talked about one hydrogen atom as having an atomic mass of 1 AMU. And oxygen, if you look at the periodic table, has an atomic mass of about 16 AMU. Well, if I have 1 mole of hydrogen, I have a mass of 1 gram. And another mole of hydrogen, another gram. And then a mole of oxygen weighs 16 grams. Because remember, in a mole of a substance, you have the atomic mass in grams of that substance. So we can talk about the formula mass of water, or the molar mass, and I want you to write that down because it's another thing I'll be saying all the time. The molar mass of water is 18 grams in every mole. 18 grams per mole is the molar mass of oxygen. What did we do? We took the atomic mass of the element times how many of that element are in the compound, and we added it to the other atomic masses of the other elements in the compound. That's how you come up with the formula mass. All right, now it's your turn. What is the mass of 1 mole of methane, which is CH4? Now, the tool you need is your periodic table. So get that out. What you're going to do is you're going to add up the atomic masses of 1 carbon and 4 hydrogens. I want you to stop the recording and give it a try. When you've got it, before you start the recording, show somebody who loves you and cares about you. All right, go. Okay, now I'm back. Let's see how you did. Let's see if you came up with the right answer. Methane contains 1 carbon and 4 hydrogen atoms. The formula mass is the sum of all those. 4 hydrogens, that's 4 times 1. Each hydrogen has a mass of about 1. That's the mass of the 4 hydrogens. And the 1 carbon, each carbon has a mass of about 12. So I get 4 times 1, which is 4, plus 12, or 16, about, grams per mole for methane. I hope you got it. Let's go on. How many moles are in 100 grams of water? All right. So remember, there is a certain mass for 1 mole of water. We just saw that. 1 mole of water has a mass of 18 grams. So how many of those 18 gram moles fit into 100 grams of water? That's the way you need to think about it. Now I'm going to let you do the math real quick, and then I'll show you how I want you to represent it on paper. Ready? Go. Okay, I'm back. Now let's check it out. So we start with what we're given. We're given 100 grams of water. So always start your problem solving with what you're given. Now the next step is going to be to divide by the molar mass of water. So here we have our 100 grams of water right here, and then we're going to multiply it by 1 mole for every 18 grams. Notice the 18 grams is on the bottom. So in effect, when I go from grams to moles, I'm dividing my grams by the molar mass. 100 divided by 18 is about 5.55 moles. So in 100 grams of water, it's much more than 1 mole, isn't it? Because each mole only weighs 18 grams. It has about 5.55 moles in it. Again, problem solving. When you want to go from grams to moles, what you're going to do is you're going to divide by the molar mass. All right? That's how we do it. Grams into moles. Divide by the molar mass. Divide the grams you have by the molar mass of that substance. All right. Now we're going the other way. Now we want to know how many grams are in 2.3 moles of butane. All right? So you're going to have your periodic table so that you can find the mass of 1 mole of butane. And then you know you have 2.3 moles of butane. So when I go from grams to moles, I'm going to actually take the moles, let me restate that. When I go from moles to grams, in other words, I have a certain amount of moles and I want to put it into grams, I'm going to take the moles I've been given and I'm going to multiply this time by the molar mass of the compound that I'm looking at. So in this case, the compound I'm looking at is butane, C4H10. 4 carbons, 10 hydrogens. Each carbon weighs 12, that's 48. Each hydrogen weighs 1. 10 hydrogens is 10 more, so 48 and 10 is 58. Now, I'm going to multiply that molar mass by 2.3 moles. Let's check it out. There's my 2.3 moles. Now, it shouldn't say grams per mole, but just moles. All right, 2.3 moles times 58 grams per mole. The moles are going to cancel, and I get my grams. There are 133.7 grams in 2.3 moles of butane. Okay? How many oxygen atoms in 200 grams of glucose? Now this one is a little bit more difficult. First of all, we want to think about how many moles that we have. If we have C6H12O6, which is the chemical formula for glucose, it weighs about 180 grams per mole. 6 carbons, which weighs 12 each, 12 hydrogens, which weigh 1 each, and 6 oxygens, which weigh about 16 each. You add those all up, you get 180 grams per mole. If I have 200 grams, I have a little bit more than a mole. So I'm going to take my grams divided by my molar mass to get how many moles I have, and then I'm going to multiply my number of moles by Avogadro's number, 6.02 times 10 to the 23rd. All right? So it turns out I've got just over 1 mole, 1.11 moles. That's the 200 divided by 180. And then I'm going to multiply that 1.11 moles of glucose times the number of molecules in a mole. So I end up with 6.684 times 10 to the 23rd molecules of glucose in 200 grams of glucose. Notice my steps. I converted grams to moles first, and then I went from moles to molecules by multiplying by the molar mass. Okay? Now, once I know that, that's how many molecules I have. But look, there are 6 oxygen atoms in every molecule. So now I'm going to take my number of molecules, which is 6.684 times 10 to the 23rd, and multiply that by 6 oxygens in every molecule. Gives me a total of 4.01 times 10 to the 24th oxygen atoms in 200 grams of glucose. There's a lot of steps there. This one is a little bit harder, but we're going to have plenty of chances to practice this. I hope you're excited, but we're going to be there. Now, in summary, we can build compounds using atoms. And how we do that could be through ionic bonds or covalent bonds. If we do them with ionic bonds, then we have formula units. If I do it with covalent bonds, then I have what are called molecules. And once I know the formula of the molecule, I can use the formula along with the periodic table to determine the formula mass of the compounds. Great work today, students. I'll see you later.